lesson, we learned about lattice energy, and that lattice energy is the energy that's needed to separate the ions in an ionic compound. And so, whenever a chemical bond is formed between a positive and a negative ion, there's a certain amount of energy needed to break that bond, and that's called lattice energy. Today, we're going to learn how to draw a lattice for an ionic compound. And so, whenever you're talking about ionic compounds, they are going to have alternating charges within them. You have your anions, which are your negative ions, and you have your cations, which are positive. And what they do is they are going to alternate their filling in. So, for example, this picture shows we have lithium positive, fluorine negative, lithium positive, fluorine negative. They're going to alternate to have the least amount of repulsion, but still have that attractive force between the opposite charges. The problem is it doesn't only have to do with the charges alternating. It also has to do with the atomic radius and the ionic radius. So remember, in atomic radius, the trend is decrease up, decrease across. But then we have to consider what happens whenever it becomes an ion. So let's look at the periodic table where lithium and fluorine are. So lithium is element number 3 and fluorine is number 9. They are both in the same period when they are neutral atoms. When they become an ion, that means they have lost or gained electrons. So lithium has lost an electron. That's why it has a positive 1 charge. So lithium normally has 2 energy rings, but when it loses that electron, it loses its outermost energy level, and it is going to take on electron configuration like helium. It is only going to have 1 energy level. Fluorine is going to gain the electron. That's why it has that negative charge. And when fluorine gains that electron, it is going to take on the electron configuration like neon. So it still has 2 energy levels. Lithium only has 1. So this is drawn correctly in the fact that they've alternated energy levels. It is not drawn correctly for the size. So fluorine should be about twice as big as it currently is. It's going to have to be a little bit larger, and you have to show that it's larger than the lithium ion. Because when it becomes an ion, they change their size by losing energy levels for cations, and then by becoming like the noble gases, which is the whole point of chemical bonding. So in this picture, it says a student incorrectly draws the following particulate model of LIBR. Explain the student's error or errors in this particular or particulate drawing. Okay. So first thing you should notice is they're not alternating, because it should go LIBR, LIBR, and then just go through that way. So that is one error. The other error is that lithium is in the second period. Bromine is in the fourth period. So right now they have lithium drawn as the larger ion than bromine, but lithium is going to lose 1 electron and become like helium. It's only going to have 1 energy level. Bromine is going to gain an electron and become like krypton. It is going to have 4 energy levels. So the size of the atoms is not correct. So if I was going to correctly draw it, I'll draw a smaller lithium and a larger bromine. Smaller lithium, larger bromine. And I would keep doing that. So then down here, I'm going to go bromine, lithium, bromine, lithium. And I would make sure that my size of my atoms were relative to each other. AP usually isn't going to make you draw a particulate drawing. They're usually going to make you could have explained this with words, or these are going to be multiple choice options. When we have an ionic solid, it is in this fixed structure. So it is in a fixed structure where the particles are not moving. That is what it means by solid, is they're in a fixed position whenever it's in its solid state of matter. If it's solid, it cannot conduct electricity if it's an ionic solid. It must be either molten, which is just melted, or it has to be dissolved in water, where those ions separate out into an aqueous solution. The particles have to be able to freely move in order for that electricity to flow. If they cannot freely move as they are in solid state of matter, they do not conduct electricity. So for example, this question says, which of the following correctly identifies whether the solid represented by the particulate matter model shown above conducts electricity, and explain why or why not. So this is obviously in a solid state of matter because it is in a fixed position and they're alternating and everything looks like it is staying right where it's supposed to and it's keeping its shape. If it was a liquid, they would be more haphazard. They wouldn't be as organized. And obviously if it was a gas, they'd be spread all around. So if it's a solid, that means it will not conduct electricity. So we know it's not going to be A or B because it is not going to conduct electricity because it already tells you that it is a solid. So we know it's not going to conduct electricity. So it does not conduct electricity because ions cannot move freely, or it does not conduct electricity because there's small spaces between the particles. Well, that is not correct. And so the correct option is C. This one goes back to the lattice energy that we talked about the other day. So this is the amount of energy it takes to break these chemical bonds. This one says that you have NaF and MgF2, and it says on the basis of Coulomb's law, which of the following best helps to explain the large difference in the lattice energies? So when you're looking at lattice energies, you want to first look at charges, then look at ion size. And so in this one, sodium has a positive 1, fluorine is a negative 1, magnesium is a positive 2, fluorine is still a negative 1. And so this one has 930 for its lattice energy. This one has 2,978. And if we think about and go back over here to look at Coulomb's law, if I have greater ion charges, I have a greater force of attraction, which means it takes more energy to break the bond. So I have greater ion charges, I have a greater force of attraction, so the lattice energy is going to be greater to break that bond. So then down here, the solubility of MgF2 is less than that of sodium fluoride. Well, solubility has nothing to do with lattice energy. The electronegativity of magnesium is greater than that of sodium. And if we think about our electronegativity trend, it is increase up and increase across. So this statement is actually true because magnesium would have a greater electronegativity than sodium. So this is what I'm telling you to be careful with. This is a true statement. It does not relate back to lattice energy. Lattice energy is based on Coulomb's law. The mass of the magnesium cation is greater than the sodium cation. That's also true, but mass is not going to be your option ever. It is, your trends are not based on the mass of the atom or the compound. The charge of the magnesium cation is larger than that of the sodium cation, which is true because this is positive 2 and that's positive 1. Even if I didn't know that, I can look at the charges and work backwards because if this is a negative 1, sodium has to be a positive 1. If there are 2 fluorines and each are negative 1, that's a negative 2. So magnesium has to be a positive 2. So my correct option is D. And then that ends this section about ionic solids. Pretty straightforward section, but a big deal whenever it comes to the properties of these different ionic compounds.